In this video, we're going to begin looking at inductors. So just like we did with capacitors, we're going to start with the basic physical structure of an inductor, and then we're going to build up towards our IV equation, and then from there we're going to look at how our inductor behaves in a circuit. The basic form of an inductor is shown here in the bottom left. We see we have a wire or some current carrying element which is wrapped around in a series of loops, or we say it creates then a coil. Oftentimes this coil is going to be wrapped around some core, so we can think of this as being a piece of metal, but we can also just have a coil wrapped around sort of air, so we have an air core. And so here is an equation where we can determine the inductance of the inductor. So the inductance is L, and I'll define each of these terms more clearly on the next slide, but we see that it does depend somewhat on the geometry. It depends on this cross-sectional area A of the coil, as well as the length of the coil. So here's our length of the coil. I will note that this equation does not appear in our textbook, at least not in the chapter 3 that we're dealing with right now, but this is a pretty standard equation for inductance. So the units of inductance are henries, so we'll use H for henries, again similar to how we used ohms and capital Greek omega for resistance, and F and farads for our capacitance. So again, a 1 Henry inductor is relatively large, but it's not uncommon to see a 1 Henry inductor. Typical ranges of inductors are going to be microhenries to tens of henries. Again, for labs here at Milligan, mostly what we would see would be microhenries or millihenries. So again, 1 Henry is a relatively large amount of inductance. So we talked a little bit about the cross-sectional area A on the previous slide. L was the length of the coil. So let's look at these other terms here. So we have this mu sub r and mu sub naught. And so these are permeabilities. So mu sub naught is the permeability of free space. And we notice that the units of this are henries per meter. Mu sub r is a relative permeability. So this is material dependent. So that's where if we have a different core material, we would have a different relative permeability, which as we can see would affect the inductance value. Just like our relative permeativity, epsilon sub r, this relative permeability is dimensionless. And then we could confirm that if we put in all of our other units, our mu sub naught being henries per meter, our A being meters squared, our L being meters, we would end up with just units of henries for our inductance. The one other parameter here in this equation is this capital N, and so N is the number of turns. So if we think back to the picture on the previous slide, we had a wire wrapped around a coil. So it's basically saying how many times do we wrap that wire around that coil.